moving forward with the special cases of simplex method, the next numerical that we have, it is given to us is that objective function as max z 4x1 plus 3x2 subjected to x1 minus 6x2 is less than or equals to 5 and 3x1 is less than equals to 11, given that x1 and x2 are greater than or equals to 0. Okay, the label of the numerical is that we have to solve this using a simplex method. So for that purpose, if as per our standard protocol, that if I convert this inequality into equalities for simplex method, it will be x1 minus 6x2 plus s1 equals to 5 and 3x1 plus s2 equals to 11. My objective function in this case will be max z 4x1 plus 3x2 plus 0s1 plus 0s2 subjected to x1, x2, s1 and s2 are greater than or equals to 0. So now if I plot all these values in my given simplex table, so we know that in simplex table the very first column is for our Cj variable. Next that I have is my basic variables. The next column is for my solution. Now in this case, if we look at the problem statement again, I have 4 variables x1, x2, s1, s2. So if I write down my basic variables, so x1, x2, s1 and s2, and their values in objective functions are 4, 3, 0, 0. So 4, 3, 0, 0, and here I have is my replacement ratio. Now if I start my first iteration for the given case, as it is of maximization case, inequalities are converted into the equalities. So first iteration, okay, the basic variables will be my s1 and s2, and their Cj values in objective functions are 0, 0. If I write my first equation here, it will be 5, this will be 1, minus 6, 1 and 0. Here it will be 11, this is 3, 0, 0 and 1. So my initial table is ready with me. Now if I make an attempt to compute the Zj values, so that will be 0 for all the cases. As such, the coefficient values of basic variables are over here is 0, 0. If I do a Zj minus Cj in this case, so it will be minus 4, minus 3, 0, 0. So the maximum negative value that I get over here is with respect to x1 variable. So it indicates that my x1 is incoming variable, x1 is my incoming variable, and this particular column is my key column. It is easy for us to understand this part. Now if I do a replacement ratio computation, it is 5 divided by 1 is 5, and here I will get 11 by 3. So I know that among these two variable, the 11 by 3 is relatively lesser value. Okay, so this indicates that this particular variable, that is my S2, it is my living variable, and corresponding to that, this will become my key row. So this part is clear to us, that we are done with our first iteration, and as a result we know that x1 is our incoming variable and s2 is our living variable. So if I write over here the values of my second iteration, so in that case s1 will remain as it is. In place of my s2, now it will be x1. This remains 0, and here it comes 4. Now if I write the values for x1 cell, for x1 row, in that case I know that the key variable has to be unity. So if I do that, so here it is 11 by 3, this is 1, this is 0, 0, this I will get as 1 by 3. So I have divided this all the values by 3. Now what I have to do is that I require to make a 0 here, and for that purpose what I need to do is that I require to multiply this row by 1, and then I have to subtract it. Means basically I have to directly subtract this. So if I do this, if I make a subtraction, if I do 5 minus 11 by 3, so I know it is 15 minus 11, that is 4 by 3. Next, 1 minus 1 is 0, minus 6 minus 0, that is 0, then 1 minus 0 is 1, and here 0 minus 1 by 3 it will give me a value of minus 1 by 3. If I make an attempt to compute the zj values, in that case this will be this is 11, so it is 44 by 3, this is my 4, this 2 remains 0 0, and this gives me a value of 4 by 3. If I do zj minus cj, so this is 4 minus 4, that is 0, 0 minus 3 is minus 3, this is 0, and this gives me a positive 4 by 3. What it indicates is that my minus 3 is still a negative value here. It indicates that corresponding to this x2 is my incoming variable. Now to compute the outgoing variable, I require to do a computation for replacement ratio. So this gives me my key column. So now this particular division is not possible, and likewise if I do a division over here, 11 by 3 divided by 0, so that gives me infinity. Okay, I am getting these two options. Now this is interesting here. In this case speciality has come. 4 by 3 divided by minus 6, as we have discussed, it is not possible. Replacement ratio cannot be negative. But now here we are facing a new situation. Earlier we have faced that 0 divided by 11 by 3, that gives us a value of 0. But now here division is 11 by 3 divided by 0. If I do this, it gives me a value of infinite, and this is also not acceptable in simplex table. So what is actually happening over here, that we have to understand now. Yes, because it gives me still a scope that one variable which still has a zj minus cj value as a negative, it indicates that this variable is still our incoming variable, but we do not have any option for our outgoing variable. So why this thing is happening, that we have to understand. So if we make an attempt to understand this thing using a graphical method for our same case, let us check what is actually happening in this case. So if I write this 2 as our inequality form, so it will give me that x1 minus 6x2 is 5, and this will give me a 3x1 equals to 11. So what are the intercepts that if I take x2 as a 0 in this case, it will give me a value of x1 as a 5. Here it will be 11 by 3 and 0. These are my x intercept. If I compute y intercept by taking x variable as a 0, if I take y intercept by taking this value as a 0, it gives me 0 and minus 5 by 6, and this remains same, 11 by 3, 0. So if I make an attempt to plot this on a graphical scale, let us check what is actually happening, that this is my x1 scale, this is my x2 scale. Now if I make an attempt to plot these two lines, so for the first line it is 5 0, and second one is 0 minus 5 by 6. So minus 5 by 6, it is actually less than minus 1, so that will be somewhere over here. So that will be somewhere over here. So this is the line that I am getting for x1 minus 6x2 equals to 5. Now talking about which particular direction we have to show, whether the region is above this line or region is below this line, because I have a negative sign over here. So if I randomly place one point somewhere from over here, let me test this variable. So this is a 0 2. So if I place the value over here, 0 minus 6 into 2, so that will be my minus 12, and it is less than 5. So it satisfies this condition. If I put this values, if I place this value, so in that case what I'll get, that 6 0 variable. So 6 minus 0, okay, 6 minus 0 is less than 5. So it does not satisfy this condition if I am putting the value, if I am putting this point, that is my 6 0. So in that case it is very clear from our side that this is the region which this particular line satisfies. Likewise, for the second line the condition is 11 by 3 and 0. So that will be somewhere over here. Yes, the 11 by 3, so 3 3s are 9. Okay, so somewhere between 3 and 4 this point will be lying, and this line is parallel to y axis, it is parallel to your x2 axis, and the sign over here, that is less than or equals to. So this is the visible region. So up till over here it is correct. Now I know that x1 and x2 has to be greater than 0. So in that case the common intersection of this two is this particular region. Yes, this is the common intersection of these two lines. Now if I look at my objective function, it is of maximization type, it is max z. So the maximum value that I am getting, okay, it is moving in a upward direction till the infinite. Yes, the possible maximum value that I can get of this objective function based on this common region is that this line indicates that above this particular region, entire region is feasible, and this line indicate, which is my, I forgot to mention here, that is my 3x1 equals to 11. Okay, so in this case the common interaction indicate that it is moving in a vertical upward direction till infinite. So this is a case of unboundedness. Okay, so this is a case of, let me write here, it is your unboundedness. So now from this particular simplex table, it is evident that when we have a case of unboundedness, what happens? Generally what happens that in the case of unboundedness, that you have a possibility that one variable may enter, because that variable has a zj minus cj value as a positive value. So that is your liable element which should enter, but you don't have any variable, which leaves your solution. So whenever in a simplex table this situation arises, it indicates that the solution is unboundedness. So this is another special case of simplex table, simplex method. Moving with one more special case, if I write objective function that is provided to us, it is max z 4x1 plus 3x2, which is subjected to x1 plus 4x2 is less than or equals to 3, and 3x1 plus x2 is greater than or equals to 12. X1 and x2 are greater than or equals to 0. So in this case we have two different types of constraint limitation. One is less than or equals to type, and second one is greater than or equals to type. So if I quickly convert them into equalities, so x1 plus 4x2 plus s1 will be 3. In this case we have a greater than or equals to sign, so we will have a surplus variable that will with the negative sign. So in that case the equation will be 3x1 plus x2 minus s2 equals to 12. But as we know that with this given condition, if we begin our solution, s2 will give a negative value, and that will be the violation of our non-negativity condition. Hence we require to add one more extra artificial variable when we have a greater than or equals to type inequality. And if I write my objective function again, it will be my max z 4x1 plus 3x2 plus 0s1 plus 0s2 minus m a1 with x1, x2, s1, s2 and a1 are greater than or equals to 0. So with this information, if I begin my simplex table, so in that case the first cell that is designated for our cj variable, these are our basic variable and solution variable column. x1, x2, s1, s2 and a1 are my basic variables in this case, and this column is for our replacement ratio. let me write here replacement ratio. This values over here are 4, 3, 0, 0 and minus m. So now if I make an attempt to fill all the cells, I know the basic variable for the first iteration will be your S1 and A1, and their values of Cj coefficient is 0 and minus m. For first row, the values are 3, 1, 4, 1, 0, 0. This is 12, 3, 1, 0, minus 1 and 1. If I write Zj variable here, it is minus 12m, this will be minus 3m, it is minus m, 0, minus minus plus m, and this will be your minus m. So if I write a Zj minus Cj, in this case it will be minus 3m minus 4, this will be minus m minus 3, 0, m minus m minus minus plus m, so that will be your 0. It indicates that this particular cell minus 3m minus 4, it is the maximum negative value, and corresponding to that this will become our incoming variable x1, and this is our key column. Now if I make an attempt to compute the replacement ratio for outgoing variable, that is 3 divided by 1, that is 3, 12 divided by 3, that is 4. It indicates that S1 is my living variable, and corresponding to this becomes my key row. Okay, so this is what we have as our first iteration, and at the end of first iteration, now we know that the S1 is our living variable and x1 is our incoming variable. So x1 and a1 are here. X1 has a coefficient of 4 and a1 has a coefficient of minus m. If I fill the cells here, the key variable itself is a unity, so in that case all these values will remain as it is: 3, 1, 4, 1 and 0, 0. To make a 0 over here, I require to multiply this row by 3. So if I do so, let me write it over here. This part is visible to us. So my multiplying factor is, in this case, is 3. So if I multiply that with this row, 3 into 3 is 9. This will be 3. It is 12. This is 3, and this 2 remains 0, 0. So if I do a subtraction now, 3 minus 9 is minus 6. Then, sorry, my mistake. 12 minus 9. Yes, 12 minus 9 is plus 3. 3 minus 3 is 0. 1 minus 12 is minus 11. Then 0 minus 3 is minus 3. And these two are minus 1 and 1. If I compute Zj here, so what I'll get is that this will be minus 3m plus 12. This is 4. This will be 11m. Yes, minus minus plus 11m plus 16. This will be plus 3m plus 4. This will be plus m, and this will be minus m. And here if I do a Zj minus Cj, so it will be 4 minus 4 is 0, 11m plus 16 minus 3, so that will be 11m plus 13. This is 3m plus 4, this is m, and minus m minus minus m, that will be minus m plus m, it is 0. So all these zj minus cj values over here are positive values, as such m is large and positive number. So what is happening over here actually, if we pay attention that we do not have any variable which is our living variable in this case, but still in your solution cell, okay, you have a presence of a1. So we have reached at optimum solution, but at the same time the solution is infeasible. So what I am stating is two different things, that I am stating that the solution is optimal, at the same time I am stating that the solution is infeasible. So what is the correct among this? Definitely this is the optimal solution, but at the same time in the basic variables I still have a1 as my present variable. This is infeasible solution. So for more clarity about this, if I use a graphical method for the same for our clarification, so we can make a suitable conclusion. So for a graphical method, if I write equations here directly, if I am writing the intersections, one is x-intercept. Let me write first x-intercept and y-intercept. So for x-intercept, if I make this, if I assume this to sign as equals to sign, x1 plus 4x2 equals to 3. So if I take x2 as a 0, in that case x1 will be 3, and if I take x1 as a 0, in that case it will be 3 by 4 y-intercept for the first line. Likewise for the second case, if I take x2 as a 0, it will be 4, and if I take x1 as a 0, it will be 12. So now if I use a graphical method for better understanding, I have many points, so let me just write them. The vertical axis I have up to 12. So this is all the points. So for the first line it is 3 0, so this is my 3 0, and 0 3 by 4, so 0 3 by 4 is actually less than 1, so it is somewhere over here. So if I draw a line over here, this will be the line for x1 plus 4x2 equals to 3, and the sign over here is less than or equals to, hence this is the sign. What it indicates is that this particular region is my feasible region in this case. Now if I make an attempt to plot the second line, that is 4 0 and 12 0. So 4 0 and 12 0 are our points, and if I quickly connect them, so this will be the line for our 3x1 plus x2 equals to 12, but the sign over here is greater than or equals to type. So if I plot it over here, okay, this will be the region, and in this case this is my feasible region. For the second case, for the first case this was the feasible region. So what we have is that we don't have any interaction among these two. So from the graphical method it is clear that this is the case of our infeasible solution. Yes, it is our infeasible solution. So now how to interpret this result? So whenever we have all these zj minus cj values as our positive values, as you can see over here, but at the same time you have a presence of artificial variable in the basic variable column. So it indicates that the solution is infeasible. So in the simplex method we have studied all the cases. That very first is your unique optimal case. Then we studied the multi-optimality condition in which in Zj minus Cj rho the basic variables have the values as 0, but along with that non-basic variable, either of the non-basic variable have their values as a 0. So that is a case of multi-optimality that we discussed in the previous video. And likewise today we discussed that unboundedness and infeasible region. In unboundedness what we have is that you still have a chance for incoming variable, but the outgoing variable is not possible. Either it is having a minus sign in the division, that is of your solution cells to the key column cells, and this value replacement value is not possible to compute. Either it is negative or it is infinite, so that indicate unboundedness. And likewise whenever we have all the Zj minus Cj as a positive values, but still you have a presence of artificial variable in your basis, so that will give you a infeasible solution indication. So these are the 4 cases that we had, okay, in the simplex method.